All right, so we have a lot of people already joined, so we'll get started. Um, Good morning, good afternoon, good evening, wherever you are joining from. We have people from different countries. So welcome to this weekly webinar series. And the purpose of these webinars is to recognize the challenges and think about innovative solutions and foster collaborations. And this webinar series is supported by ISNGE Environmental Geotechnics Committee, ASCE Geoinstitute Geoenvironmental Engineering Committee. So I am Krishna Reddy from University of Illinois at Chicago. So this is our fall 2025 webinar schedule. Today we have a very interesting presentation, and then you can see, other presentations that are upcoming. So they're all on different topics, and presenters are all experts in those topics. The past webinars have been recorded. You have this YouTube channel. You can go and look at the previous webinars, and you can view them. Again, they are all on a wide range of topics. Today's webinar topic is very interesting. I know that's why we have a lot of registrants for this webinar. Already so many people have joined the webinar. So introduction to cone penetration testing and advanced CPT modules. And we have presenters, Garrett Davis and Bruce Miller. Garrett is a regional manager for the company ConeTec in Chicago area. So he got BS in geological engineering from University of Mississippi, and he worked in the field for many, many years. Bruce is the business development director, again with the company ConeTec, and many people who know CPT or who are familiar with CPT, they should know about the company ConeTec. And so, and Bruce got his BS in geology from Laurentian University, and he served as a regional and branch manager, and he has been with the company for 26 years. ConeTec has done, wide range of projects throughout the U.S. Bruce particularly worked on projects in the northeastern and midwestern U.S. as well as eastern Canada. And ConeTec has worked on many notable projects. For example, Gateway Tunnel into Manhattan, all three New York City airports, Tappan Zee Bridge, Second Avenue Subway, World Trade Center, and many noteworthy projects. So ConeTec contribution is in every major project, and of course, they deal with a lot of other projects all over the U.S. and in Canada, and now it's being used in worldwide. AEG, Association of Engineering Geologists, Chicago chapter, organized a workshop, cone penetrometer technology workshop on March 29, 2025. And I attended this one along with my couple of students. It was, very nice presentation by ConeTec and other presenters. And here is Bruce, demonstrating ConeTec and showing all the features of CPT. I really admire ConeTec for taking their time and educating the profession and also demonstrating. This takes a lot of effort to bring the truck and put everything together and actually show, all the different features of ConeTec. So I really admire Bruce and ConeTec and Garrett for outreaching and educating people about CPT. So today for this webinar, we have 857 registrants from over 40 countries. So please mute your mic and switch off your video. At the end of the presentation, I will ask you to show your video so that we can have a screenshots of people who are attending. And then I request you to type your questions in the chat box, or you can raise your hand. I will ask you to unmute and ask question. Our presenters will answer as many questions as possible within the time that we have. If you are looking for a certificate of participation or one PDH, you must attend the entire webinar. That's the first thing. And second thing is you need to fill out the Google form. A link will be posted in the chat box towards the end of the presentation. So you must fulfill these two requirements to get the certificate of participation. So again, I want to thank Garrett and Bruce for agreeing to present this webinar in spite of their hectic schedule. And thank you all for joining this webinar. And let's all learn from this webinar. With that, I want to stop sharing, and I request Garrett to share the screen and start the presentation. Thank you so much, everyone.
And thank you, Dr. Reddy, for the invitation.
Yes, thank you for that wonderful introduction. My name is Garrett Davis, and I'm co-hosting today's webinar with Bruce Miller. We both work for ConeTec here in North America, and we're going to introduce the topic of cone penetration testing, or CPT, and speak a little bit on the advanced CPT modules you can add on to the cone penetrometer. We'll start today with a brief background on CPT, get into the specifics of the cone, what data is collected, and then we'll finish with the additional modules and the various deployment methods of the cone penetrometer. So geotechnical engineers rely on various in situ tests for accurate soil characterization. This hour we'll be focusing on the tests and the equipment inside the red box, the cone penetrometer. CPT stands out for speed, repeatability, and offers continuous profiling. So let's define what it is. Cone penetrometer testing is a geotechnical investigation method used to determine properties of soil in situ. It involves pushing a cone-shaped probe into the ground at a constant rate and collecting data. Where can you use CPT? Anywhere soils exist. It can be deployed on various sites, from construction sites to environmental cleanups, bridges, dams, buildings, etc. A little history on the cone penetrometer to start us out. So CPT started back in the 1930s with the mechanical Dutch cone. A couple decades later, the friction sleeve was added in the 50s. Electronics were introduced in the 60s, and piezometers followed in the 1970s. Seismic CPT was introduced in the 80s, and in the 90s and 2000s, we used analog cones that converted voltages at surface to data points, and today we have digital cones that perform the computations downhole. Moving into the future, we're beginning to integrate automation into our test procedures and use machine learning on CPT data sets. So let's look at the components of the modern cone penetrometer. Today, the standard cone penetrometer should include sensors for tip, QC, friction sleeve, FS, and for pressure transducer, U. The cone may also include geophones, thermistors, inclinometers. All of ConeTec's cones include the suite of sensors. Moving on to the standards that govern CPT testing across the world. We've got ISO 22476 internationally, and here in North America, the standard for CPT is governed by ASTM D5778. As we know, these standards define procedures, calibration, and reporting, and by adhering to them, it allows for comparable and repeatable data. So we'll just briefly touch on both of these. Among other aspects, the ASTM standard defines the lowest acceptable resolution of data, or 1 data point every 5 centimeters. At ConeTec, we collect standard rate of 2.5 centimeters, and there are smaller intervals available if higher resolution is required, down to data point every centimeter or less. We'll briefly touch on the ISO standard here. The current standard was updated a few years ago, and this version introduces changes to the testing, calibration, and classification of the soundings. Like the ASTM, the ISO covers the calibration protocol, field procedures, and also defines dimensional tolerances for the tooling. As you can see, in order to conform to these standards, your CPT probe would have to include the necessary sensors to measure the required attributes, such as temperature, verticality with your thermistor and your inclinometers. And in order to ensure they're compliant with these standards. So now let's review some testing basics. So the procedure, the cone is prepared by checking and recording exterior dimensions of the cone, cleaning the internal O-rings, then a saturated pore pressure filter is added to the cone behind the tip before the sleeve, and the cone is then hung vertically under zero load to record your initial baselines. The same is done post-sounding to record your final baselines. Next, it's lowered to the ground surface, where it will begin with the tip at the surface. It's deployed 2 centimeters a second, continuously measuring the tip, sleeve, and pore pressure. Once you reach target depth of refusal, you pull the tooling, take your final baselines, and abandon your hole according to local regulations. In roughly an hour, you can complete a 20-meter or 65-foot CPT with no additional testing. So next, we'll look at the importance of recording pore pressure. There's various types and sizes of cone penetrometers with various sensitivities. The CPT cone can come with or without pore pressure transducers. All of ConeTec's cone penetrometers are type 2 and use a pore pressure transducer in the U2 position or shoulder position, as we said, directly behind the tip before the friction sleeve. If you don't record pore pressure, you lose the ability to make corrections and normalize your data. So it's an important parameter to measure for accurate and reliable calculations. We'll see why this matters in the next couple slides here as well. So when we push a cone into the ground, we're collecting QC, the measured uncorrected tip value. Most equations call for QT, or corrected tip. So we use the equation on screen, which accounts for the pore pressure acting on the cone tip geometry. In the equation, U2 is the dynamic pore pressure at the U2 position, and A is your net area ratio. The net area ratio is the surface area affected by fluid pressure divided by the cross-sectional area of the cone. So we can see greater A value, less corrections applied. And note the caution at the bottom of the screen. In some older literature, QC is used where they should actually be using QT. So if you're reading some old papers, keep an eye on that. Here's a visualization of the forces in action here. On the left, you can see the cone penetrometer without your pore pressure filter. In the middle, it's taken place of that space. And on the right, you can see the forces acting on the tip, the QC measured, and the pore pressure pushing back on the shoulder of the tip there. Again, we're measuring QC, correcting for QT by adding in or subtracting a fraction of pore water pressure. So this measured QC doesn't account for those fluid pressures acting on the cone shoulder, and calibration determines the net area ratio in a fluid-filled vessel. For example, we push the cone into a vessel with known 100 units of pressure. We witness the tip QC only recording 80 units of pressure. So we've got to correct for the missing 20 units of pressure that were not captured by the tip alone. Correcting this by adding a fraction of the pore pressure back gets us to QT from QC. And each cone geometry, whether it's 10 square centimeter, 15 square centimeter, needs its own calibrations. Now let's move on to soil behavior type. Moving away from pore pressure, soil behavior type classification allows you to infer the soil material by analyzing its response to cone penetration by comparing it to the behavior of known soil types. SBT, or soil behavior type, can be charted graphically, and it's a tool that's used in cone penetration testing to classify the soils based on how they respond rather than just the grain size or their composition. SBT uses CPT measurements, the cone tip resistance, sleeve friction, and pore pressure to estimate whether the soil is behaving like clay, silt, sand, or gravel. This improves geotechnical modeling by linking CPT data to engineering properties and supports the design and decision-making for foundations ground improvement etc. Here we'll look at a basic CPT plot. We've got boxes shown from left to right. We've got our measured tip, our measured sleeve friction, calculated friction ratio, and our measured dynamic pore pressure. Then on the far right, we've got the soil behavior type. This plot shows zones of unsaturated sands on top of transitional materials. We've got a sand lens, and then we've got some intact clays there at the bottom of the profile. You can see in the column second from right, the dynamic pore pressure, that in these intact clays, you've got dynamic pore pressures roughly 2 to 3 times hydrostatic. The red line on the plot box on the far left denotes 50 TSF or 50 bar, which is roughly the dividing line between clays less than 50 and sands greater than 50. And we're using the SPT QTN chart from Robertson in 2009 on this plot, and you can see how these materials are then classified as such. Soil behavior type is the basis for advanced interpretations. It classifies soils into categories of sand, silts, and clays, and supports your design. So for example, if we take a data point here, roughly 150 TSF and a friction ratio of approximately 0.5, and we come to our soil behavior type chart, we've got normalized friction ratio here, friction ratio here. The chart on the left is not normalized, and the chart on the right is normalized. We would go to 0.5 on our friction ratio and about 150 on the tip, which plots us in zone 6, this tan colored material, which is calling clean sands or silty sands, and we can see that's what our CPT plot is showing us as well, based on the soil behavior type. There's a myriad of different charts that have been developed over the years, and here's a few different ones. We've got the 86 chart on the left, 1990 chart moving right. We've got a BQ chart, a BQ normalized chart, and then that 2009 chart we were looking at earlier. If we compare these SPT charts versus a normal bore log, you can see that if you take samples at discrete intervals, you may overgeneralize a large chunk of your subsurface when there may be smaller lenses and changes of material present there that is picked up by the CPT that's not necessarily picked up by sampling every 2 meters or 5 meters. Another example of an SPT chart is this BQ chart. It uses pore pressure and tip resistance, unlike the previous charts that use the friction ratio or sleeve stresses. This chart is useful for refining soil classification beyond the tip resistance and friction ratio, and does a better job at classifying clay soils with excess pore pressure. As we can see back here, the non-BQ charts are classifying this middle layer as primarily silts and mixtures, and the BQ charts pick out those clays a lot better. Continuing on with the theme of pore pressure, we'll discuss pore pressure dissipation testing during CPT soundings. Dissipation tests are used to determine local phreatic surface and help assess soil permeability and consolidation. So to perform a PPD test, you first must be using a cone with a pore pressure transducer. Then you would stop advancing the probe into the ground, and at that point, the pressures will begin to equilibrate. Depending on the material, the dissipations will take shape of the typical pore pressure versus time plots that are shown here in the middle of the screen. We've got clean sands on the top, typically hydrostatic dynamic pore pressure. So when you stop, there's not much change. Normally consolidated clays begin with a high pore pressure, elevated pore pressure, dynamic, and when you stop, the pressure dissipates. Dilated materials like sands and silts will rise and equilibrate in that third plot from the top, and the bottom one, fine grain dilative materials, will rise and then fall. From these PPD tests, you can calculate time rate of consolidation. This is a typical normally consolidated response in clay. And to get to your time rate of consolidation, you first determine your U50, or your point at which 50% of the pore pressure has dissipated. U50 will then allow you to find T50, which is the duration of time it took to reach U50. You can put those into the calculation for C sub H, along with a time factor, your cone geometry, and a rigidity index to get your C sub H. So moving past the tip, sleeve friction, and pore pressure data, cone penetrometers can also be outfitted with geophones, as we discussed before, and those can be used to collect seismic data. All of ConeTec's cones have at least one geophone embedded in the body, and it allows for the collection of seismic shear and compression waves. From this additional data, you can determine shear modulus, soil stiffness, and liquefaction potential for your site. The procedure to collect this data, the cone is advanced into the ground at the standard rate of 2 centimeters per second. At every 1 meter or desired depth increment, the penetration is paused. At that point, a seismic source at the ground surface, usually a hammer strike or weight drop, generates a wave. The geophones inside the cone detect the arrival of the shear compression waves, and the time difference between the wave arrivals at successive depths is used to calculate wave velocities. So this process repeats every meter or interval, building a continuous shear and compression profile for your entire sounding. Here we see a CPT seismic plot. The far right plot box is plotting those velocities that we collected at those intervals. And the circles mark the midpoint between two tests where shear waves were collected, and the vertical line shows the average velocity over that interval. When dealing in feet per second, we like to show 600 feet per second, which is the dividing line between seismic site class D, or stiff soils, and E or F, soft soils. So let's look at some real data. On the left, you've got your shear wave profile, VS, and on the right, you've got your compression wave, VP. You can see in animated boxes how each of the wave types propagate through the subsurface. Also note the distinct change in the velocity at around 25 meters on the right profile of the compression waves. The slope changes at approximately 25 meters, and the compression waves start coming in at the speed of sound through water because it's fully saturated. So at 15 meters per second, or about 5,000 feet per second, is the speed of sound through water. So we can conclude in this plot that we have dry or partially saturated soils above 25 meters, and below 25 meters, the profile is fully saturated. I'll touch briefly on data reporting. As we talked about, we're collecting tip, sleeve, pore pressure, shear wave, compression wave. And with those relatively small number of parameters, you open up a world of calculations and interpretations. So earlier we looked at our standard CPT plot briefly. These standard plots display roughly the same information that's monitored real time during your data collection. This plot also includes the SPT QTN bars on the far right and colors the tip plot box according to those soil behavior types. Now we'll glance at some advanced plots. we'll talk here. So ConeTec includes an Excel file in our reports with 90 plus calculated and estimated geotechnical parameters. Estimated unit weights are used based off the soil behavior type chosen, and those are combined in calculations, which reaffirms the importance of using the right SPT for your site and to have the ability for your cone penetrometer to collect all of the desired measurements. So here's an advanced plot. Any of those calculated geotechnical parameters can be plotted. In this one, along with the corrected tip, the dynamic pore pressure, we've got IC or CPT material index, we've got undrained shear strength estimates, estimates of friction angle, and estimates of blows per foot. So in theory, you can tailor your advanced plots to show what's most important for your investigation or your individual site. Another plot here shows a different profile containing surface fill over some clay and then clean sands. This is a good example of dynamic pore pressure in clean sands following the hydrostatic line. Here you can see the dynamic pore pressure in the material below about 28 feet roughly follows this hydrostatic line. These triangles here denote some pore pressure dissipations, which confirm this. We also see in this profile, compared to the last one, where we've got a lot of estimated undrained shear strength here. In this profile, we've got a lot less, but we've got more estimates of friction angle. This is also a great example of the ability of the cone penetrometer to advance through, 40, 50 plus blow count material. Some of our cone penetrometers have the capacity to measure up to 1,000 or 1,500 bar, and other cones exist with much lower capacities that are used to classify more sensitive sites like lake sediment. So there's various ways you can report and play around with the CPT data once you've collected it. Use it in models, create your tailored plots, perform interpretations, etc. So at ConeTec, we've got an in-house team that handles the processing and reporting of our CPT data. A full comprehensive data report is made available at the end of every project through ConeTec Data Services, where you can play around with your CPT data in some of these programs. And as we know, there's other processing and interpretation software available both publicly and privately. So in summary, the CPT delivers stratigraphy and groundwater data quickly. It helps assess strength, stress history, and settlement potential. It supports liquefaction analysis and foundation design, and it's a rapid test even in dense soils, as it's governed by the ASTM and ISO rate of penetration. And the cone can be combined with various other in situ test instruments. So we'll get to some add-on modules here now. Some additional modules you may add to the cone penetrometer for some environmental sites may be the UVIF, or the ultraviolet induced fluorescence, the UVOST, ultraviolet optical screening tool, the HPT, or hydraulic profiling tool, MIP, MIP, or membrane interface probe, EC, electrical conductivity and resistivity, and the OIP, the optical imaging probe, among others. So these add-on modules are attached to the tool string directly behind the cone penetrometer, and they may include sensors for, as we talked about, electrical resistivity, volatile organic compound and solvent detection from the MIP, permeability, your K value from HPT, and even radioactivity by using gamma logging. We'll touch on a couple of those here. First is the MIP, or the Membrane Interface Probe. It's a logging tool that measures volatile hydrocarbon and solvent contamination along with soil electrical conductance and permeability. Usually the MIP also has an EC and an HPT included. The process is an inert carrier gas is continually swept behind a heated membrane in the probe, delivering it to a series of detectors at the surface. The detectors each respond to different analyte properties. This allows the MIP operator to discern the contaminant to its family group. Here we can see the probe. We've got the HPT sensor here, the MIP membrane, and the CPT probe at the bottom. Then we've turned it 90 degrees so we can also see the EC dipole that's included in this probe add-on attachment. So that you can combine them to do all three. Compared to CPT, the production of MIP plus HPT EC is a little bit slower. This is due to the test procedure calls for stopping each 1 foot interval, which allows that heater block to heat up and volatilize the compounds, which are then sent uphole. This takes a little bit of time, so your production rate is decreased. Here we're looking at a plot that has EC, electrical conductivity, on the far right and moving, or far left, excuse me, and moving right. We've got the HPT, our hydraulic profiling tool, our PID, which is the photoionization detector. Then we've got the XSD, which is the halogenated chlorinated detector. And then the FID, which is the flame ionization detector. And finally, we've got our estimated K. Here we can see this particular profile contains some uncontaminated sand sitting on some contaminated clay-like material, which is sitting on top of uncontaminated clay. So performing multiple soundings across site provides the ability to map out your contamination plume from source to extent. And obtaining an understanding of the soil conductance and permeability along with the contaminant information allows the user to know the VOC contamination, if it's near to the prominent migration pathway or not, or if it's bound up in a storage zone. This all aids in how the investigator should approach site remedial efforts. Moving on to the resistivity or conductivity add-on probe. It can be added behind the cone penetrometer, and there are also cone penetrometers with this equipment built into the barrel. The module is typically located about 0.8 meters behind the cone tip, and it measures the electrical resistivity of the soil and pore water. Dipole or ring electrodes are used to measure the resistivity, which is influenced by your soil type, moisture content, porosity, and the chemistry of the pore water present on site. On the right here, we can see a plot of a sounding of resistivity. So combining the two provides high resolution continuous profiles of your subsurface conditions. Applications for resistivity CPTU may be detecting contaminant plumes by detecting changes in resistivity, corrosion potential assessment, ground densification quality control. So you run your RCPTU before and after your ground improvement. And it can also be used in saltwater intrusion studies, detecting salinity changes in coastal or reclaimed land areas. Here we've got a plot where we've combined everything we've talked about so far. The hydraulic profiling tool, electrical conductivity modules fall onto the cone penetrometer. Theoretically, you can add on however many modules you desire. Here in this particular plot, we can see elevated concentrations of this chlorinated substance showing up at the bottom of this plot. So we may want to set some monitoring wells or take some samples. Moving on to UVIF CPTU. This uses ultraviolet induced fluorescence to excite hydrocarbons through a sapphire window, and the probe detects the fluorescence. So the presence and absence is what the UVIF will generally give you. You've got contamination here between 10 and 12 meters, and then roughly between 15.5 and 16.5. Above that, we've got relatively uniform response. So it's not going to tell you exactly what it is, but it'll give you relative concentrations that then will prescribe your drilling program or your sampling program. Some advantages: you're collecting data every 2.5 centimeters, same as the CPT. You get real-time data and use it to optimize your site investigation. You go out with this first, poke a few holes, determine your contaminant plume, and then that drives your sampling. Another add-on probe that also uses a laser is the UVOST, or ultraviolet optical screening tool. It's similar to the UVIF, where the module contains a window in which a laser is emitted into the soil. But this particular laser pulses at different wavelengths, which can be used to identify contaminant types, aging or degradation of the contaminants, and relative concentrations. It uses the 4 wavelengths there on screen, and that helps us determine typical responses, where you'll get a waveform that's bluish green, and it's most likely gasoline. Jet fuels are blue, diesel is green, etc. So the probe picks up the presence of the contaminants in direct contact with the window, and the resulting waveform can be viewed real time on screen. The primary function of the UVO system is to identify LNAPLs, or your floaters, such as we said, gasoline, diesel, jet fuel. So here's an example of a UVO CPT plot containing both your standard CPT parameters and the continuous UVOS response. In this instance, the UVOS plot box has replaced our friction ratio, and we can see the spikes in the middle of the plot from the response. And comparing this to a known sample control, we can determine this is gasoline. Typically, you'll want to have a control to compare your responses against if you have an idea of the contaminant. Here's another plot here where we've pushed UVOS CPT. We've got the water table here shown, and we've got what looks to be like some weathered or decayed contamination that's had time to dry out in the not fully saturated part of this profile. And then below it, we've got another similar response that we were able to determine is gasoline. Below that, we've got relatively low responses. We would think that the contaminant is hung up here on your water table as its floater, and you'd likely want to do your sampling in the first 5 feet or 1.5 meters below the water table. So the advantages, it's rapid and cost effective. It's almost as fast as the CPT. There's a little bit more setup, but you don't have to stop, such as when you're doing MIP and HBT, so you can continuously profile a little more efficiently. And like we said, most of these add-on modules optimize your targeted drilling and sampling and monitoring wells. So moving away from the probes, we'll wrap things up here, showing you some of the equipment and ways the cone penetrometer can be deployed on sites like yours. We've got land-based CPT rigs, the classic truck rig. We've got track rigs, and we've got combos. We've got a truck track, we call it, there on the far right. You can drive on the tires to get you to site, and when the conditions get a little questionable, you can drop your tracks down and you've got a versatile machine. You can also push CPT from direct push rigs like geoprobes. We can push them from the truck on a bridge as long as we've got some support casing there supporting the rods. And you can also push it on the back of a drill rig. There's rail units available. Both of these are of the same machine, but we can get, you can add rail units to any truck that can perform CPT and work on those types of projects as well. We've even got now hybrid EV machines. You use the diesel tier 4 engine to drive the machine to your site. You turn off the engine and then you work on battery power, pushing your CPT, running your dissipations, pulling your tooling. And then when you want to move on to your next site, you turn the engine back on, which charges your battery as you're driving, and you keep on pushing. Also portable ram sets. They can be mounted to drill rigs, sonic rigs. They can be added to an excavator mount to push vertically or even inclined or horizontal pushing. And there's limited access ram sets, smaller, more portable ram sets that 2 people or 1 person could move around. They can be brought into the basements, bolted to concrete slabs. Out on a lake, they can be anchored into the ice, and you can test those lake sediments down at the bottom without needing to get a boat or barge out there. You can even use them on the cantilever setups. And then various marine and overwater applications, barges, jackups, even boats with dynamic positioning systems. And if you're really in some deep water, you can drop this equipment down. It's called a ROSON. It allows you to set that system down on the seafloor and control it remotely, pushing CPT with your crew on surface, the tooling all down at the bottom of the ocean. And when you're done, you pull it all up with a large winch. And before we go on to questions, just want to inform you of some recent and future webinars that you can attend or watch recordings of. We did one a couple days ago talking about the ISO standards we touched on. And coming up, there's a software demonstration on CPT. You can scan the QR code or go to the link below. Thank you.
Thank you. Thank you so much, Garrett. That was very nice presentation. You covered all kinds of aspects related to CPT. So I request everyone